we'll try to compute the pressure of a liquid of height h at a particular point. So our objective of this particular video is to compute pressure of a liquid of height h and density rho. Okay, so let us consider a vessel. And the vessel is filled with, let's just say, some liquid. We don't know what the liquid is, but we have been given the density of the liquid. So let's just say we have a vessel which is filled with a liquid of density rho, and the height of the liquid column is given as h. Alright, now let's take 2 points on this vessel. So let's take point A. I suppose this is a darker color. Let me take a lighter color. Okay, let's take pink. I guess pink will be visible. Yeah, so let's take a point A and a point B. So our objective is to compute the pressure at point B. Okay, so pressure at point A will be the atmospheric pressure because it is an open vessel. So it will be a atmospheric pressure. I'll just write it as PATM. Usually at sea level the atmospheric pressure is 1 atm. So you could consider it to be as 1 atm as well. Now we need to calculate the pressure at point B. Alright, so our pressure at point B, which will be the summation of PA and the pressure due to the liquid column of height h. Alright, so our objective of this video is to find this particular pressure, which is pH. Alright, so let's make a small FBD, or a force body diagram, of the liquid column. So I'll just try to draw rather. Yeah, I've selected this particular liquid portion. I'll zoom it in like this. So this is the liquid column. Okay, now let me draw the force body diagram of the liquid column. Alright, the force exerted of the liquid column is downwards, which is mg. Alright, this is the force. Okay, so let's calculate the force. I can write this force to be as m into g. G is the acceleration due to gravity. Okay, in the given is the density of the liquid as rho. So I can write mass as density of the liquid multiplied by the volume of the liquid. Okay, how am I getting this particular equation? Since density is mass upon volume, I can say that mass will be equal to density multiplied by its volume. Okay, so force becomes density multiplied by volume multiplied by gravitational acceleration due to gravity. Alright, now in order to compute pressure, I need to divide force and area. Alright, so force becomes density of the liquid multiplied by volume. Volume could also be written as area multiplied by its height. Okay, so how am I, okay, let me just talk about this for a moment. How is how is volume of a vessel area multiplied by its height? For example, let's just say I have taken a cylinder. So the base of the cylinder is a circle. Okay, and the area of the circle is pi r square, and the height of the cylinder is h. So you might have studied in your earlier classes that volume is nothing but pi r square multiplied by h. So this is not this is actually pi r square is the area of the base multiplied by its height. So I'll get force as density multiplied by volume. Volume is basically area multiplied by height into acceleration due to gravity, and I have divided this entire equation by area. Now the area will get cancelled out, and I'll be left with the equation of rho, which is density of the liquid multiplied by height multiplied by acceleration due to gravity. So this is the pressure at point B due to the height of the liquid column. So this is nothing but pH. So if I have to compute PB, it will be equal to P atm, yani atmospheric pressure, plus rho GH. Talk about the next part of the video. In this we'll talk about certain rules that we need to follow in order to understand the next part of the topic. Alright, so let's start with the rules regarding pressure. So the first rule is that pressure at the same horizontal level will be equal. Pressure at the same horizontal level will be equal. Now what this means is, let's just say I've taken a vessel okay, and I have poured some liquid on this vessel. Alright, some liquid at this vessel, and I've taken a few points on this vessel. Alright, so let's take these 2 points. Let me call that point A and this is point B. Okay, since they are at the same height, okay, or the same horizontal line, I can say that A and B are both at the same horizontal line. I will say that the pressure at point A will be equal to pressure at point B. Alright, and if I take another set of 2 points, let's take point C and point D, which are also at the same horizontal level, I will say that the pressure at point C will be equal to pressure at point D. So there will not be any pressure difference if we move horizontally along a line, but pressure difference will arise only when we change the height of the point. For example, as we go downward in the liquid column, the pressure will increase because the height of the liquid or the mass of the liquid gets added up. So I will say that the pressure at point C will be more than the pressure at point A. Why is it so? Because at point C, the liquid is applying a much more force at point C than at A. At point A, there is only the pressure of the atmosphere. At point C, there is the pressure of the atmosphere and of the liquid. So there is some part of liquid, there's some part of pressure due to liquid that is getting added up. So I will say that pressure at point A and point B are equal, and both are less than the pressure at point C and D. Okay, this is the first rule that you need to understand, which is, if the surface of the liquid column is in any way exposed to the atmosphere, okay, is exposed to the atmosphere, then I will write that then pressure along the surface, or at the surface will be equal to the atmospheric pressure. Now let's take a small little example. Alright, I'm going to take 3 different test tubes. Alright, so let's take 3 different test tubes. My drawing really isn't that great, so pardon me for this, but I hope you're able to understand what I'm trying to say in this. Alright, so let's say I have filled this particular test tube with some liquid, okay, and I wish to calculate the pressure at point A. Okay, and let's take another example where I have completely inverted the test tube. Okay, and the liquid here is kind of inverted as well. Okay, and then I need to find the pressure at point A again, and let's take another example of the test tube which a little slanted. Okay, and this is also filled rather with the same liquid which has been inclined at an angle of 25 degree from the imaginary horizontal line. Alright, so for this also I need to find out pressure at point A. Okay, so for each of these diagrams, the pressure at point A will be equal to atmospheric pressure. Atmospheric pressure. Okay, so it doesn't matter how they are placed and at what angle they are, as long as the liquid is exposed to the atmosphere, the pressure at, sorry, pardon me for this, I'm yet to buy the zoom. Yeah, upgrade. So yeah, so the pressure at point A will be atmospheric pressure. Again, pressure at point A will also be atmospheric pressure, and the pressure at point A will also be atmospheric pressure. So if the surface of the liquid column is exposed to the atmosphere, pressure at the surface will always be equal to the atmospheric pressure.